Hello, everyone. We are now heading to our part 6.2, dealing with geoid models in Canada. Just a reminder about the topics. We are going to basically discuss the different geoid models that have been used in Canada, the different vertical systems used in Canada. It's the geoid in Canada has grown in importance because for a vertical reference system, it has been adopted as a vertical reference system. So that's what we're going to discuss, among other things. A reminder about the references that we have for this chapter, and also a reminder about different papers that are available on Desire to Learn papers, and there is one presentation. And I want to emphasize the last one there, which is in the additional references, number 7. It's a very nice review paper on vertical datums. So let's just make a link to what we discussed last time. We talked about the how we can connect the heights that we get from GNSS, the geodetic heights, also mostly called popularly as ellipsoidal heights, and then the orthometric heights, which are basically the heights that we want to use, and it is done by means of the geoidal height. So we need to know the geoidal height in such a way that we can transform the heights that we determine with GNSS, which are not physical. They're purely geometric. We cannot use them for in height applications, for example, in water applications. We have to transform them to the orthometric heights. And we also discussed that we can do that differentially. We can compute the difference of orthometric heights if you know the GPS heights or the geodetic heights between 2 points, GPS or GNSS. I just have been generic here, and we have to get the difference of geoidal height from a geoidal map. And I show you this very old map, geoidal map in South America, in Brazil. This is basically how we used to do. We used to go interpolate with the pen, the tip of the pencil. Now, of course, things have progressed, but let's have a look at how things progressed in Canada. So Canada has gone from a tidal base vertical system to a geoid based vertical system. It's actually it was the pioneer in the world in this respect. So until 2013, Canada adopted the Canadian Geodetic Vertical Datum of 1928, which is known by the acronym CGVD 28. It was adopted officially in 1935, and I have to make a comment on the normal orthometric height. And if you recall, when we presented orthometric heights, we mentioned that to compute the so-called orthometric correction, we need to know the mean surface gravity between two benchmarks. Now, what happens is that in practice, sometimes leveling was done and no gravity was observed. So to bypass that, it was the trick was to use the normal height. Okay, so in essence, the orthometric heights were mixed up, and to avoid these, well, to make sure that people would understand that fact, the fact that not all orthometric heights in the network were actually computed based on actual gravity, but on normal gravity. NRCan, who is the concerned with responsible for taking care of a vertical system, decided to refer to the heights as normal orthometric, which is a kind of a misnomer, but nonetheless it's a way to indicate that it's not a purely orthometric height system. Now, in the meantime, lots of effort have been placed in terms of developing geoidal models for Canada. We know geoidal models are important because of transformation from GNSS heights to orthometric heights. So all this effort led to the development of the Geodetic Survey Division, GSD, models. And we have also the so-called Canadian gravimetric geoid, which are more recent. So essentially, the Canadian gravity geoid of 2010, which is the current one, the Canadian Geodetic Model 2013, is a further improvement from that. But we can take the CGG 2010 as a good reference. The uncertainty in terms of the geoidal heights, you can see they are at the centimeter level. For example, New Brunswick, we have an absolute value of centimeter level in terms of absolute precision, and with 1 sigma. Okay, so we are going to look at that at the next table. The CGG 2013 was then adopted as the new vertical datum. Now, the assessment of models, we have to have an idea in terms of the accuracy. The best we can do is to compute the geoidal height by doing GNSS survey over benchmarks. So benchmarks, we know the orthometric height. We then determine the geodetic height from GNSS, and from here we can compute then the geoidal height. Just a important observation that Canada never adopted the NAVD88, the North American Vertical Datum, which is actually was built to be a continental datum, but it served just for the use in the continental US. And by the way, the Americans are working towards adopting a geoidal model also as a vertical datum. So they are basically following the footsteps or what we have done. As a matter of fact, it is there is a lot of collaboration between the agencies, the National Geodetic Survey in the US and the Canadian Survey Division here in Canada. This table, it's actually an analysis of the CGG 2010, but give us a very good idea in terms of the absolute accuracy. Okay, I'm calling accuracy because the comparison here is with GPS on benchmarks. And again, GPS provides the lowercase h, benchmarks give the capital H, orthometric. The difference between them gives the geoidal height. So we can then compare the geoidal height extracted from a geoidal map with the geoidal height that have been extracted from GPS on benchmarks. So as a matter of fact, we have, okay, well, let's look at this one here because this is what we're really interested with. Here we have EGM 08, 08. These are different models. The US model of 2009. But here is, so the same comparison, but this is what we want. Okay, we want to look at this one here. So what we have that for the whole Canada, south of the parallel 58, we have a difference of 115 millimeters. That's quite high. And now, if you do the authors of this study, they did a filtering of the data, and they got a final value of 49 millimeters. So that's basically 5 centimeters. For BC and Alberta, they got, let's look at this final here, 45. They don't differ that much. Vancouver, just the region of Vancouver, it's 22 millimeters. So we're talking here about a centimeter level geoid. In the Rockies, we have the highest source of error because of the mountains. In the prairies, we have kind of a 4. It's a high level, even though it's a plain. It's a plateau. The Great Lakes, 4 centimeters. Lake Superior, Lake Ontario, South Ontario, Lake Superior, and we go all the way here to the Maritimes. And the Maritimes, that's the number that I use. It's 3.6 centimeters. Well, give or take 4 centimeter. So we are dealing with a geoid that for the southern part of the country of Canada, it is at the centimeter level, and if you go north, then we go to the decimeter level. Now let's look at the Geodat Survey Division 95 geoid, just an example. Okay, let's look at here. I don't know if you can see, but Canada is here. This is, well, that's for Canada. If you look closely, you can see the contour lines. And let's focus here. This is Hudson Bay. And if you look at the scale here, this is a negative value of geoidal heights. These are positive values of geoidal height. We can see here that in this portion of the country, we have predominantly negative geoidal heights, and then we have a growing value. They grow from the minimum to the maximum as we move to the periphery. And actually, this thing here, it stretches more into North America. So the geoid in Canada, if you make a plot of the current geoid, it's going to look pretty much the same in its overall shape. The interesting thing is that in this area here, that's a phenomenon known as post-glacial rebound is taking place. If you remember, we discussed that. That's the huge mass of ice from the last ice age that was removed very fast, melted very fast, and the Earth is still rebounding. So this rebound is actually we can see on the geoid. Okay, it has left a mark on the geoid. So because the crust is going up in this region, what happens is, of course, the value of the geoidal height is also being modified. So, which means the geoidal height varies with time. Here is the rate of change of the geoid, again related to the GSD 95, and we can see here this is the amount of how much it subsides and how much it raises. So it goes from 1.5 raising in the white areas. So the white area is exactly here. The maximum is on top of a Hudson Bay, and it decreases. And we can see that in the periphery we have actually it's going down. Okay, here about 0.5. So that's why I tell you that Nova Scotia is going down. Sorry, guys, and also Vancouver here somehow. So which means this area here is going up, and the periphery goes down. And the funny thing is, not funny, but the interesting thing is that this region here, in more towards the south of the U.S. and north of Mexico, is stable. It's not going down, neither up or down. It's just stable. So that's something that's very interesting. We can see the signature of the last glaciation on the geoid. The internal precision, now this is the value, the standard deviation of the adjustment, and the internal precision, it will give us for most of the country values that are around 2 centimeters, which mostly would be slightly more optimistic than the accuracy that we got from comparing GNSS on benchmarks. We can see, of course, that in the west coast, which is very mountainous, the precision is much higher. Okay, I mean, the precision is much less, it's less precise because of the mountains. Okay, we have to apply topographic correction, and that becomes, creates more difficulty. So that's normal. That's something that's normal. So it's a quite decent geoid. It's actually very good work that we have done. And just incidentally, I should mention to you the solution that NRCan has used is based on the Stokes-Helmert method, which basically has been formulated here at UNB. And there was a comparison of different geoidal map computations recently done. And in the last International Union of Geodesy and Geophysics meeting in Montreal last year, the results were presented, and the best performance geoid model was the one based on the Stokes-Helmert method, exactly the one that was developed, that was coded by NRCan. So yay, we have the best geoid. Here is the Canadian vertical network. So basically, each red line represents a road or a highway. As you know, leveling, we go through the roads, and this is a very extensive network. It is we cannot compare the network of Canada with, say, Switzerland or Germany. Well, to begin with, the size of the countries, but if you look at the effort that has been placed in Canada, is just tremendous. So we are talking here about decades of geodetic leveling and gravity observations on benchmarks, and these would be the basis of the Canadian vertical system of 28. Okay, something that is interesting to mention that, okay, a lot of this leveling was done by former survey engineering and then geomatics engineering students from UNB. They would get summer jobs to go and do leveling with NRCan. What is unfortunate is that with the adoption of the geoid model, Canada, the federal government, decided not to maintain the leveling network. So, which means that the leveling, the benchmarks, a benchmark that is destroyed, it is not replaced. So there is no more leveling done at federal level. This is unfortunate because we can do lots of interesting studies based on the releveling, looking at the leveling done in the 1930s, then with leveling that was done in 1980s. We can see crustal movement. And also, as we mentioned, the leveling network is a way to validate a geoid model. So if by doing GNSS on benchmarks, if there are no GNSS, no benchmarks anymore, we cannot do that. So that is a little bit of a sadness on this, but that's what is happening. I don't see that changing in the future. So here we have the network of GPS observations on benchmarks. It doesn't cover the whole network, but it spatially covers everything. I mean, so we can see the. I mean, it's a very good, and if you look at this map, you can see we can evaluate very well the geoid in the southern portion of the country. Okay, if you go north, we don't have geodetic leveling there, so we can really not validate the geoid except in the Yukon with a few lines there. Okay, how do we relate orthometric height and the geoidal height, aka ellipsoidal height in Canada? So the best thing is to use the official software, the official solution that is connected, of course, with this CGG to 2013. It's a program called GPS-H, which converts ellipsoidal heights to orthometric heights or vice versa. And here is the link. You can have access to it. You can use it online, or you can download the executable. And the indicated precision of the solution varies around the country. So here's a snapshot of the graphical interface online. It is quite simple. We can choose the vertical datum. We can choose the geoid associated with it. We can choose the reference frame, and here we can use an AD83 and or any one of the ITRFs. We can choose the epoch that we are interested in, and then we can also choose. Okay, so the input, the first red arrow there, if the default is input in geodetic heights, but if you want to input the orthometric height, you can. So here we have the we can use geographic, or should call geodetic coordinates and Cartesian coordinates, and or the UTM or modified UTM or the stereographic double projection. So the latitude, longitude, I just plug in numbers there. I put 0 geodetic height, so we are basically on the ellipsoid. And here the result gives the orthometric height, in this case the epoch, and here is the N, which is the geoidal height, with indication of its precision. So it's saying that it's a plus or minus 1 centimeter, and this is 1 sigma. The value of gravity, this is an interpolated value, and here we have the dynamic height. Okay, which is something very interesting. You know that for water applications, the orthometric height is okay, but the best height system would be dynamic height. And here we can see actually the difference. From this arbitrary point here, we have a difference of 1 centimeter between orthometric height and dynamic height. So, the geoid in Canada, the vertical frame in Canada is now a geoid. It's a gravity-based vertical datum. It differs from the old datum, the CGVD28. Okay, and if you look at this figure here, this diagram tries to represent the difference that we have in terms of mean sea level, and this is important. Oh, the geoid is the mean sea level, but there are other factors, as we're going to discuss, that also affect the mean sea level. So the Pacific Ocean in the West Coast is slightly above the Atlantic Ocean in the east. Okay, so Nova Scotia is down from BC. I don't understand, but anyway, in terms of mean sea level, of course, not in terms of the beauty of Nova Scotia. What we have here is in green we have the geoid, okay, the Canadian geoid. So there is a difference of 40 centimeters in the east coast and a difference of 14 centimeters in the west coast. So we're going to see how that impacts. The fact of life is that currently the zero value of that would be where the sea connects with the earth, our geoid is not going to give zero perfectly. Okay. Anyway, there are the variations of tides, etc. That doesn't. I mean, it's Bay of Fundy. It's plus or minus 11 meters with the tidal. Well, 11 meters up and down with the tides. One thing that I strongly recommend you guys to do is to keep track of what goes on, and there are easy resources available. NRCan, the Geodetic Survey Division, has lots of material. Here I have, I indicated in the previous slide the link, and this is the link that talks about the modernization of the height reference system. So it is important because the current geoid will change, okay? As we know, we saw how the geoid varies with time, and there is going to be need for an update. This update will come, I don't know, in 20 years, 10 years, who knows. But the fact of life is that it's important for you to keep track of that. Okay, so with that we end this part, and have fun.